Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis of both discrete time as well as continuous time, Fourier analysis for periodic as well as aperiodic signals, alright. And we have looked at the theory corresponding to that, and now let us start, and in this module we are going to start looking at various problems to better understand the implications and applications of the Fourier analysis for continuous time signals that we have seen so far. Okay. So, let us start by our looking at example problems for Fourier analysis, that is the Fourier analysis of continuous time signals and systems. All right. And so, let us start with problem number 1, which is basically consider the signal xt equals cosine (2t plus pi by 4). We want to obtain its complex exponential Fourier series, or what we can abbreviate as the CEFS. We want to obtain the CEFX for this given signal, that is xt equals cosine 2t plus pi by 4. Now, what you can observe here is that from this you can observe that the period, okay, so this is cosine 2t, alright. So, omega naught equals 2, which means the period, the fundamental period of this equals, well, 2 pi by omega naught, that is equal to t naught, which is equal to 2 pi by 2, which is equal to pi, okay, and omega naught equals 2. So, I can express this as xt, this is the CEFS representation, k equals minus infinity to infinity Ck e raised to j k summation k equals minus infinity to infinity Ck e raised to j k omega naught t. This is the complex exponential Fourier series, or the CEFS, where Ck denotes the coefficient, the complex coefficient corresponding to the kth harmonic, correct, that is the frequency component, which is k times omega naught, where omega naught is the fundamental frequency, okay, t naught is the fundamental period of this periodic signal, okay. And now, rather than evaluate this directly, evaluate the coefficients directly, we can see that I can evaluate this as xt equals, I can directly evaluate this as xt equals cosine 2t plus pi by 4, which is e raised to j, cosine x is cosine of, well, cosine theta is e raised to j theta plus e raised to minus j theta divided by 2. So, this is e raised to j 2t plus pi by 4 plus e raised to minus j 2t plus pi by 4 divided by 2, which I can write as half e raised to j pi by 4 e raised to j 2t plus half e raised to minus j pi by 4 e raised to minus j to t, which is equal to C1 e raised to j omega naught t plus, you can see this is C minus 1 e raised to minus j omega naught t, where this coefficient C1, now you can see this is basically your C1 and this is basically your C2. So, C1 is basically this coefficient. So, C1 equals, well, half e raised to j pi by 4 equals half, well, e power j theta is cosine theta plus j sin theta. So, e raised to j power pi by 4 is half is cosine pi by 4 plus j sin pi by 4, which is half 1 over root 2 plus 1 over root 2, which is 1 plus, of course, 1 plus j over 2 root 2. Okay. So, this is C1 equals 1 plus j over. So, the coefficient C1 in the CEFS is 1 plus j over twice square root of 2. Now, similarly, C minus 1, that is coefficient of e raised to minus j omega naught t or minus j 2 t in this case, is C minus 1 equals, well, half e raised to minus j pi by 4, which is half cosine pi by 4 minus j sin pi by 4, which is basically half 1 over root 2 minus j over root 2 equals 1 minus j over 2 square root of 2. Okay. And you can clearly see from this that, from this you can clearly see that all Ck, that is because since this is expressed simply as a combination of e raised to j 2 t and e raised to minus j 2 t, all the terms Ck for k not equal to 1, that is C0 as well as C2, C minus 2, C3, C minus 2, etc. so on are 0. So, Ck for any k not equal to either plus 1 or minus 1 is basically 0. Okay. So, all the coefficients, so Ck, the rest of the Ck equal to 0 for all mod k not equal to 1, that is either k equal to plus 1 or minus 1. Okay. So, that is the complex exponential Fourier series and these are the coefficients. So, this is the coefficient C minus 1 in the complex exponential Fourier series and this is the coefficient C1 in the complex exponential Fourier series. Okay. Now, let us look at a periodic sequence or a periodic square wave. So, let us look at this is example number 2 in which we want to look at a periodic square wave and a periodic square wave can be represented as follows. So, you have a square wave which is periodic. So, this is of width T naught by 2 and this has a period of so this has a period of T naught. So, this is minus T naught over 2. So, this is your periodic square wave, correct. This is your periodic square wave, and the time period here equals T naught, and let us say the height is equal to height of each square pulse, or the peak amplitude of each square pulse is 1. And what we want to do is, for this periodic square wave, we want to find the complex exponential Fourier series and also the trigonometric. Remember, there is an alternative Fourier series representation which is known as the trigonometric Fourier series. We want to denote this by TFS. So, we want to find the complex exponential Fourier series and as well as the trigonometric Fourier series representation for this periodic square wave, which has square pulses of height 1, width T naught over 2, and fundamental period is T naught. Okay, all right. And this can be done as follows. Now, first observe that the fundamental period equals T naught, which implies omega naught equals 2 pi over T naught, and this implies that xt equals summation. So, I can write the CFS as xt equals k equals minus infinity to infinity Ck e raised to j k omega naught t. So, this is your CFS representation, the complex exponential Fourier series, because this is periodic with T naught, omega naught equals 2 pi by T naught. This is the CFS representation. Okay. And now Ck, the coefficient Ck can be found as, remember, is 1 over T naught integral, you can find it as 0 to T naught or any period t of duration T naught, contiguous period of duration T naught, in fact xt e raised to minus j k omega t naught, omega naught t dt, which is basically, we know that in the period 0 to T naught, xt is simply a pulse of height 1. In the period it is non-zero, in the period T naught 0 to T naught over 2, and in that it is a pulse of height 1. So, this is xt will be 1 in 0 to T naught over 2 e raised to minus j k omega naught t dt, which you can see is basically 1 over T naught e raised to minus j k omega naught t by minus j k omega naught t evaluated between the limits 0 to T naught over 2, which is 1 over T naught e raised to minus j k e raised to minus j omega naught T naught over 2 minus 1 divided by minus j k omega naught, I am sorry, this has to be minus j k omega naught. Okay. And now realize that we have omega naught equals 2 pi by T naught, which implies omega naught T naught equals 2 pi, and therefore, this from this the expression for Ck can be simplified as, look at this, in the numerator we have omega naught into T naught by 2. So, omega naught into T naught by 2 will be pi, and the denominator we have T naught into omega naught, that will be 2 pi. So, this will be 1 minus e raised to minus j k omega naught into T naught by 2 is pi divided by j k omega naught into T naught equals 2 pi. So, this is the expression for the coefficient Ck which is the complex exponential Fourier series coefficient. Okay, all right. So, this is Ck is 1 minus e raised to minus j k pi divided by j k into 2 pi. All right, and we have used the principle that omega naught t naught equals 2 pi, omega naught t naught over 2 is simply pi. Okay. And now you can observe that e raised to minus j k times pi is nothing but minus 1 raised to the power of k. Okay. So, this is e raised to minus j k pi is basically e raised to minus j pi raised to the power of k, which is nothing but minus 1 raised to the power of k. So, this if you see, this is e raised to minus j pi, okay, this is e raised to minus j pi raised to the power of k, which is basically minus 1, which is basically minus 1 raised to the power of k. So, Ck equals 1 minus 1 raised to the power of k divided by j k into 2 pi. Okay. And now you can observe that if k is even, implies if k is equal to 2m, this is equal to C of k equals 1 minus 1 to the power of 2m over j into 2m pi. Now you can see 1 minus 1 to the power of minus 1 raised to the 2m is 1. So, this is simply 0. So, Ck is 0 if k is even, and if k is odd, implies k equals 2m plus 1, then Ck equals 1 minus 1 raised to 2m plus 1 divided by j 2m plus 1 times pi, j, or in fact j twice 2m plus 1 times pi, j or twice j into 2m plus 1 times pi equals 2 over 2j into 2m plus 1 pi, which is nothing but, in fact this is C of 2m plus 1, k equals 2m plus 1, C 1 over j times pi into 2m plus 1 for any, therefore for any odd k, equal to 2m plus 1. For any odd k equals 2m plus 1. Okay. So, for even k it is 0, for odd k it is 1 over j pi 2m plus 1, and the DC coefficient, remember C naught that is corresponding to k equal to 0, that is termed as the DC coefficient, which is simply 1 over T naught times the integral over the function over the interval of duration T naught. So, this is 1 over T naught, that is the average, time average of the signal 0 to T naught xt dt, which is basically your 1 over T naught, again this is non-zero, only in 0 to T naught over 2 times 1 dt, which is basically 1 over T naught into T naught over 2. So, this C naught is equal to half, and therefore, finally what we have is basically we have xt equals half plus 1 over j pi summation m equal to minus infinity to infinity 1 over. So, this exists only for even k, that is of the form 2m plus 1. So, 1 over 2m plus 1, I have taken the j pi outside since it is common, e raised to j 2m plus 1 k omega naught t. or I can just write, let me just write it once more a little clearly. So, x of t equals half plus 1 over j pi summation m equal to minus infinity to infinity 1 over 2m plus 1 e raised to j 2m plus 1 omega naught t. So, that is your, so this is your complex exponential. This is basically the complex exponential Fourier series representation. Okay, so this is the complex exponential Fourier series representation of the signal. All right. So basically, what we have done in this module is we have started looking at problems for the Fourier analysis of continuous time signals and systems. All right. In particular, we have looked at an example which basically finds the Fourier complex exponential Fourier series of a simple signal followed by the complex exponential Fourier series of a periodic square wave. Okay. Of a square wave, and we are also going to the subsequent module, we will also find the trigonometric Fourier series representation of this. All right. So, we will stop here. Thank you very much.